Can you hear me?
Yes, sir.
Yes, sir.
Okay, so let's start. Uh, so in the last class, we discussed and derived about the electric and magnetic field for an arbitrarily moving point charge. If you remember the expression that we have obtained, so first I'm writing the electric field and magnetic field for a moving point charge. Electric and magnetic fields for uh, an arbitrarily or moving point charge with arbitrary velocity. Moving point charge. Can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir. Okay. So let me just first write down the expression for electric field and magnetic field, and then proceed further. So the electric field for a moving point charge at location R at some time t was given by charge time curly r vector, scalar vector. Curly r is basically the distance between the field point and the moving point charge at any given instant, divided by 4 pi epsilon 0, which is a constant, and then curly r dot u. You may remember the definition of u. I will write it again. Cube into c square minus v square. C is the speed of light, v is the velocity of the moving point charge, u, I shall write it again, u plus curly r cross u cross a. A is the acceleration. And what is u? U, we defined u to be c times the unit vector r cap minus v. This is u. This u is given by this expression. This is u. Now, and the magnetic field. Okay, so let us write down this in terms of say, because in relativity we write beta and gamma in place of v and the Lorentz factors. So let us write down in terms of beta. That will be convenient if we work specifically in the relativistic regime. And for that, let me just rewrite these expressions a little bit in different way. So if you write u to be in this way, then what will be ru? R times u, r times vector u, right? So then I c times r, so that will be c vector r minus r times v. If I take c common, c will be outside. Inside I will have vector r minus v by c, that will be vector beta r times vector beta, beta vectors basically. And then r dot u, we have the r dot u here. You see r dot u. This is r times this vector u. That's why I wrote it this r times this vector u. And we have a r dot u in the denominator. So let us write down that also in terms of beta r dot u. If I take a dot product of r with u, so this dot this, so I'll have c times curly r scalar r minus r dot v. We already know this, right? So c into, if I take common, r minus v by c is again beta, so r dot beta. So I shall write down this entire expression in terms of beta. But again, this doesn't make any difference. And only thing is that it will be a little bit convenient. Again, you can keep this expression, I mean, if you are comfortable with this. Okay. So what will be electric field then in terms of this? So let us write down that E electric field R T is equal to, so I'm taking r inside this, and c square minus v square, you can rewrite that, you can take c square common, that will give you 1 minus v square by c square, which is beta 1 minus beta square. This c square can be taken outside, and this r dot u, we have already written that in this way, so I am just rewriting this again. So q by 4 pi epsilon 0 is a constant, and then inside third bracket, this is 1 minus beta square, 1 minus beta square, and then I have taken this scalar r inside, so ru will be this one, but there is a c here, and I have taken a c square common, right? So we have c cube in the numerator. So 1 minus beta square times vector r minus scalar r times beta into c cube. Now in the denominator we have this r dot u, which throws out a c here. So when you take a cube, we will have another c cube. So that c cube and the numerator, c cube in the numerator will cancel out. So 1 minus beta square times r minus r beta divided by r minus r dot beta whole cube. This c cube has been cancelled. Okay, plus কি আছে r, I have taken this r inside, so this r into u here, so I'll have plus r cross this r into this middle u, that will give us ru, that is c times r minus r beta. So there is a c here. Okay, remember that I'm not writing this c, that because that will also cancel out. So r minus r beta, and acceleration is beta, acceleration is basically velocity, derivative of velocity. So if I divide it by c, I can write it beta dot cross, remember I have introduced a c here because there is no c here, so I have taken a beta dot, so that's there is a c here, so I have to multiply by c, this one is there. Okay, and then in the denominator what we have is this whole cube, r dot u cube, that is again c cube times r minus r dot beta cube. But remember there was a c here and there was a c needed here, so c into c square, and in the denominator we have c cube, so c square c cube, so one c is left in the denominator, right? C into r minus r dot beta whole cube. This is the expression for electric field for a moving point charge. You can again write down the expression for magnetic field by rewriting the expression for B. You may remember the expression for B, but what I will suggest, once you remember E, we have already seen that B can be obtained by simply taking a cross product. What is that? 1 over C R cap ERT, right? This will give you the magnetic field. So don't need to remember the magnetic field separately. Just remember one expression. That will be sufficient, right? So just take a cross product. So that will give us Q divided by 4 pi epsilon 0 C times, we are taking a cross product, right? So we have a minus sign here, minus 1 minus beta square, and then r cross r cap cross r will be 0, right? And then we have a minus of this, so r cap cross beta, but a minus sign there. So that will be, if I want to absorb this minus sign, then I will write beta cross r, right? I want to absorb the negative sign, that will be beta cross r, because r cap times scalar r is vector r. So beta cross r into 1 minus beta square divided by this r minus r dot beta whole cube plus, I'm taking a cross product with r cap with this entire thing. So let us write down them separately. R cap, no, this is r, I have a r here, r cap here, and what we can do, well, I can write down everything in terms of r cross. Okay, okay. I can introduce the r in the denominator. That will make it easier. So let us do that. Undo. Okay. So what I'm doing, I'm writing a r vector here. That's not a problem. You can write r cap as well, but just to look it more simple. Again, the expression is not simple, but this will help me in future calculation. R minus r beta cross beta dot, you see I have written r here, not r cap, so I have to divide by a r in the denominator. So that's why, because I have written a r vector, so I divide it by r, and then whatever was there, c times r minus r dot beta whole cube, right? So this is the expression for magnetic field. Now look at these two expressions carefully, right? So these are two very important expressions. So these two expressions gives us the electric field and magnetic field for a moving point charge, which is basically moving with an arbitrary velocity along any arbitrary direction. So then what can be inferred from these two expressions? Clearly, if you look at these two expressions, there is one important feature which is easily noticeable, is that you see there are two different terms. One term, you see, one term purely depends on velocity. You see, beta is velocity, velocity of the moving point charge, right? On the other hand, the second term, you see, that depends on velocity, but it has an additional dependency on the acceleration, this beta dot. So the charge particle could be uniformly moving, or it could have acceleration or deacceleration. If it is uniformly moving, clearly you can see the second term will be zero, because beta dot is zero in that case. So we will be left with only the first term in both cases. The electric field and magnetic field both will only contain the first term, right? Because there is no acceleration or deacceleration. So beta dot will be zero, second term will be zero. And that's why these first two terms, this first term in electric field and magnetic field are often called the velocity field, although it is not representing velocity, and one should not get misguided by name. Velocity field means the field, electric field and magnetic field, that is produced by only the velocity of the, or due to the velocity of the moving point charge. And this second term, if you see, when the charge particle is accelerating, right, then we have this, right, because this beta dot is non-zero, right? So if beta dot is non-zero, then the second term is there, and this second term is called the acceleration field, or sometimes radiation field. Why radiation field, that I will explain. So this is the first term is velocity field. This is the velocity field due to only velocity. You see, this is called velocity field, and this is called acceleration field. Okay, in both case of electric field and magnetic field. And you see, in general, both the terms should be present if the charge has a non-zero acceleration or deceleration. But if you look at the terms carefully, you can see that the terms depends on the r vector in a different way. For example, look at this expression, right? If I ask you what is the dependency on this curly r is the basically separation between the field point and the moving point charge. How does the first term depend on r, and how does the second term depends on r? Do they depend in the same way, or the dependencies are different? ফার্স্ট টার্মটা আর এর উপরে কিভাবে ডিপেন্ড করে?
1/r².
1/r², right? And the second term?
r এর সঙ্গে ভ্যারিয়েবল r হবে।
ভ্যারিয়েজ আর হবে? ভালো করে দেখো, মানে প্রপোর্শনাল টু আর বলছো? এটা কারেক্ট বলেছো, 1/r, রাইট? এই জাস্ট দেখলে বুঝতে পারবে যে দেখো এগুলো বিভিন্ন অ্যাপ্রক্সিমেশন তুমি নিতে পারো যে কোনটা কখন ভেলোসিটি বেশি কখন ভেলোসিটি কম, সেটা ঠিক আছে, বাট জাস্ট বাই লুকিং এট দ্য এক্সপ্রেশন ইউ ক্যান সি দ্যাট দিস r is there. You see this whole term is, you have a cubic term here, right? The denominator cubic term. On the numerator we have only this r are separate, here r cross r আছে. So simply this will be 1/r. So the velocity term, the second the velocity term, the first term, this first term proportional to 1/r². Second term proportional to 1/r. What is the significance of this? You see, if I asked you that calculate the power emitted by this electromagnetic field or this moving point charge. And why this moving point charge? There's some physics behind that we can discuss based on the time available to us. But from simply just looking at the electric field and magnetic field, if I give you an electromagnetic field which are orthogonal, you see E and B are orthogonal. If you look at this expression, E and B are orthogonal. So if E and B are orthogonal, if I ask you what is the radiation coming out of this point charge, you can simply calculate the Poynting vector that is known to you. I mean, the formula is known to you. What is the Poynting vector? S 1 over mu 0 E cross B. Now, E is electric field, M is magnetic field, right? Of course, S is a function of RT, E is a function of RT, B is a function of RT, which I am not writing here. Now, consider when there is no acceleration, okay, it's only velocity. Now, how the Poynting vector, what is the Poynting vector? It is a physical meaning, the energy emitted per unit area per unit time. So that quantity, how does that depend on the this radius vector r? If you look at this expression 1 by r square here, the first term reduces to 1 by r square. So even without taking into consideration all the terms over there, if I just simply ask you how the Poynting vector depends on r, what will be your conclusion? How the Poynting vector depends on r? Poynting vector proportional to কি লিখবো? How does it depend on r? Already বলেছো. First term 1 by
1 by r to the power 4 minutes.
1 by r to the power 4, correct? 1 by r to the power 4. Now, if I ask you, calculate the total energy emitted by this point charge. টোটাল এনার্জি যদি বার করতে হয় কোথাও, কি করতে হয়? পয়েন্ট চার্জটা মুভ করছে, পয়েন্ট চার্জটা এখানে। সো হোয়াট ইউ ডু, this basically the energy emitted per unit area per unit time, right? Unit area. So suppose if I take a sphere of radius say r, suppose this is the field point and this is the field point. So field point is here, so this is the field point P located at a distance r here. Anyway, জায়গা নেই এখানে. So if I imagine a sphere of radius say r, okay, imagine this to be a sphere. This is not looking like a sphere at all, but anyway, this r. So if I ask you what is the total energy emitted, so if you have a say some receiver here, you can measure the amount of energy per unit area, that is the Poynting vector given by the Poynting vector. And if I ask you what is the total energy emitted by this moving point charge, now what will you do? You know the energy emitted by unit area. So you have the total area is known to you. How much is the total area? 4 pi r square. The area of the sphere is 4 pi r square, right? So total energy, if I ask you total or I mean power means energy per unit time. So I'm just considering the total power emitted. So what is the power? The power is given by this Poynting vector multiplied by the area, right? Because per unit area then multiplied by the area, it will be only per unit time. So if I multiply then to calculate the power, what will be that? See this, there is r square here in the area. So if I multiply the Poynting vector with the area of the sphere, what do I get? How the power depend?
1 by r
1
square.
by r square.
Right, power will be 1 by r square. তার মানে যেটা বলছে যে energy emitted per unit time, that will decay as 1 by r square, right? So it's inverse square, so it will fall very fast. So if you go say I have a moving point charge here of say some point charge, say 1 Coulomb charge moving here, whatever, it's some point charge, and if I go say 1 kilometer away from that moving point charge, the amount of this power radiated by the moving point charge will be negligibly small. If I go to 2 kilometer or 3 kilometer, it will be even smaller. If I go to 100 kilometer, it will be negligible, almost zero, 1 by r square. You can see, right? You know how 1 by r square goes, right? So it will fall away very quickly. Now let us go to the second term. As you have already mentioned, that second term goes as 1 by r. So I don't need to explain anything now. You already have possibly understood. Now then you see in this case, in the second case, how the Poynting vector will depend on r. It will be
1 by r square.
1 by r square, correct? the power emitted by the point charge will be, how does it depend on R?
Does not depend.
Does not depend on R. It does not depend on R. It will be completely, I mean, even if you go to infinite distance, right, it will not depend on R, right? So you will have some finite amount of radiation from the moving point charge, even if you move to infinity. Even the field point, if I take this field point to infinity from the moving point charge, even then you will get a finite amount of radiation from that moving point charge. And that is the important thing here. You see, for an accelerating moving, for a charge with acceleration, you have both the terms, velocity term as well as acceleration term. Now, since the first term is negligible, because if you go to a large distance, even medium distance, the first term is negligible. The contribution coming from the first term is negligible because the power goes as 1 by r square. On the other hand, the second term, since it goes as the second term goes as 1 by r, so the total energy emitted by the moving point charge per unit time will be nearly independent of r. So you will have a finite amount of radiation coming from the accelerating point charge at any point in the universe. It is expected, right? So you'll get a finite amount of radiation. So that's why the second term is very, very important when you discuss about the radiation coming from an arbitrarily moving point charge. You see, uh, we have already derived the expression for a uniformly moving point charge using Lorentz transformation earlier. You can verify that the first term will be the same as the expression that we have derived earlier. The second term is something new to us. The second term in both electric field and magnetic field, this is new to us. And in a general scenario, we expect that this arbitrarily moving point charge will produce a non-zero radiation at any point, at any distance, right? So this expression is very, very important, that you should remember, right? And now we shall use this expression for electric field and magnetic field to analyze radiation coming from moving point charge. Now there are a couple of things, because you see, you may wonder that how a point charge is giving rise to electromagnetic radiation, right? This is mathematical. I am getting some expression of E and B. I am taking cross product. Okay, that has some physical significance. That's the pointing vector, which describes some radiation. That is fine. So there is an underlying, physical mechanism which can be discussed. But let me first focus on the mathematical derivation, because unless we derive the expressions, we will not be able to discuss these things. So today I shall discuss about the moving this radiation coming from moving point charge. Okay, another thing I should mention here, which I forgot to mention, that you see, suppose the charge is not moving at all. Okay, so that means if the charge is not moving at all, then it's a static case, right? So velocity is zero. You can see this, all these terms will be zero. V equal to, so I'm not writing here, you just can understand it clearly. If velocity is zero, the charge is static. So this c beta will be zero, this beta will be zero. So the only term, this will be all zero, because it's cross beta dot, acceleration is zero, so everything is zero here. Here in this, for the first term, you see there is a this curly r vector, and we have a r cube, this scalar r cube, and this will be zero. So electric field will be q over 4 pi epsilon 0 r cube, just and a curly r over here. So that is Coulomb's law, that you know for a static case. And you see the magnetic field, in case of magnetic field, it will be zero. That is known to us. In a static case, these two expressions reduces to these two, right? And you can also verify that for a very small velocity, say v is much less than c, for v is much less than c, okay, for a uniformly moving point charge, you just take these two expression, and you can show that you get this Coulomb's law and the Biot-Savart's law. That is just okay. Maybe I can show it. You can do it yourself, but again, okay, let me just discuss for completeness. So v much less than c, uh, what are the expression? Okay, let me just write down this. So E, what was E? E was Q by 4 pi epsilon 0. Then we have R minus R beta I'm just writing the velocity term, not the acceleration term. Uniformly moving point charge r minus r dot beta, okay, cube, okay, and b is q by 4 pi epsilon 0 c square times this was okay beta. Okay, I have taken c here, so it will be b cross r. That was beta cross r actually. The c was taken here, so I am writing into 1 minus beta square divided by r minus r dot beta cube. Okay, you can write it beta. If I write one c here, it will be beta. Okay, no problem. So now, if v is much less than c, then you see this mod of r will be much greater than r beta, and also I am not writing it. R dot beta is scalar, so it will be mod of r will be greater than r beta as well. Sorry, yeah, mod of r beta as well as r dot beta. So electric field will be simply equal to q by 4 pi epsilon 0 r vector divided by r cube, and magnetic field will be simply q by 4 pi epsilon 0 c square into v cross r. That's why I wrote it to be v, because v will be required here, divided by r cube. This is negligible. These terms are negligible. 1 by beta is negligible when beta v is much less than c. It's non-relativistic case, and you can see 1 by epsilon c square. You can write it in terms of mu 0. So I can write this to be mu 0 by 4 pi, and then I'm writing I dl cross r by r cube. How? I is dq dt, dl dt is velocity. You see, I is dq dt, dl dt is velocity, and dq integral is q. And this 1 by epsilon 0 c square is mu 0 by 4 pi. So this is nothing but Biot-Savart's law, and this is nothing but Coulomb's law. So what we have derived is the general expression for electric field and magnetic field, from which you can obtain the static case or the Coulomb's law, Biot-Savart law. Everything can be derived from those things. Okay. Now, what we are interested in is this radiation, the nature of radiation that we get from our arbitrary moving point charge. So let us discuss that. So let us start with the non-relativistic case first, and then I shall discuss about the relativistic case. Okay, let me go to the next page. It will be better. So first I shall discuss about the radiation from an accelerated point charge at non-relativistic velocity or at low velocity. When velocity is, I mean, non-relativistic, that is v is much less than c. Okay, I mean when you can take beta almost tends to 0. Okay, it's not 0 definitely. It tends to 0. So what was the electric field for this accelerating point charge? So let us call this ER, because this gives rise to electromagnetic radiation. As I told you that the electric field and magnetic field both have two parts. One is velocity field, another is acceleration or radiation field. So that's why I'm writing ER. ER means electric field corresponding to radiation for the moving point charge. QER equal to Q over 4 pi epsilon 0 C. So I'm writing the second term here. First term, why I dropped the first term? First term is not of any importance if I want to discuss about electromagnetic radiation coming from the moving point charge. Right? That doesn't give rise any I mean physically measurable any radiation from the moving point. This is the second term. The same expression that we wrote earlier, but only the second term that I am writing here. This is the ER, electric field for the accelerating point charge, second term. And what is BR? Of course, BR, once you know ER, BR is simply R cap cross ER by C. That is known to us. Now let us analyze this electric field and calculate the pointing vector and try to understand the nature of radiation. I mean, how the radiation should look like, in which direction it should be emitted, and so on. Okay, so using this approximation that V is much less than C, that is beta tends to 0, we can write down electric field ER of this moving accelerating point charge to be Q over 4 pi epsilon 0 C. This is R, okay, R, and I told you that if V is much less than C, that is beta is much smaller than 1, it's not 0, much less than 1. Okay, then I can write this R is much greater than R beta, right? So then this term can be dropped, this one. So R cross, see, these two are inside the bracket because these two, second term and third term, they came together. If you remember how this term appeared, the second term and third term appeared together, and then a cross product was taken with the first term. So it will be R cross. Okay. Otherwise, you get confused that R cross R is 0. Okay. R cross, it is not a A cross B cross C beta dot, right? Divided by, you see, this term can be again dropped. Then under this approximation, I can write down R, which is mod of R. So again, curly R will be much greater than R dot beta, right? So then this one divided by R cube. We may also want to get rid of this R. If I just use R cap here, R by R is R cap. So I'm writing Q over 4 pi epsilon 0 C. Everything is written in terms of R cap. So here I can write R cap. R vector R by scalar R. R cap cross beta dot divided by 1 R is left here. Okay, let it be this one. So A cross B cross C. Now let us take a cross product between these three vectors. What will be that? B A dot C, B A dot C minus C A dot B, which is R cap dot R cap divided by R. This will be equal to, maybe I can also, okay, let us understand the meaning of this term, because what is R cross, what is the direction of R cross beta, okay, let me just draw a picture here that will be, I think, convenient. Let us draw suppose the moving point charge has the acceleration along these directions. Moving point charge, this is the moving point charge, and suppose this is the acceleration vector A, okay, maybe equal to, say, beta dot, okay, or A by C, okay, maybe they both mean the same thing. Well, acceleration divided by C is beta dot, okay, beta dot or A, whatever, in this direction. And suppose the field point is somewhere here. This is a field point P, okay. So then the radius vector, this curly R, should be pointed towards this direction, okay, or maybe I can write this to be R cap. P somewhere there, out there, okay. So this is R cap, and the angle between the acceleration of the point charge and the radius vector is, say, suppose theta, right? Theta. So let us now analyze the directions. So R cap cross beta, this one. R cap cross beta, this one. What is R cap? The R cap is pointing towards this direction, and beta dot is along this direction. So R cap dot beta, what will be the direction? R cap cross beta, R cap and beta perpendicular to the page, right? Take a cross product. This is R cap, this is beta dot acceleration. So R cap cross beta dot will be along which direction? Perpendicular to the page or the screen here. And what will be the direction of R cap cross beta? See, R cap cross beta is already perpendicular to the page. Okay, it is perpendicular to the page. R cap cross beta dot is perpendicular to the page, right? And then you take a cross product of that vector with R. So what will be the direction of r cap cross beta? R cap cross this, yeah, this one, sorry, r cap cross beta কোন দিকে হবে এটা?
বিটার ডাইরেকশন বরাবর।
বিটা কিছু নেই এখানে, বিটা ডট, এটা ঠিক বলছো? ভেবে ভেবে বলো। Okay, maybe I should redraw the picture once again in the next page. Okay, let me maybe এখানে জায়গাটা কম হচ্ছে, আমি আবার বলছি। This one is the moving point charge. It has an acceleration along this direction. This is the acceleration beta dot. This is the direction of the field point. The field point is located somewhere there. This is r cap. So r cap cross beta dot. This is perpendicular to the page, right? That you have agreed, right? Now what I'm asking I'm asking you to calculate r cap cross that vector. So r cap is কোন দিকে আছে? r cap এই দিকে, আর এটা পারপেন্ডিকুলার দিকে। তাহলে r cap cross beta কোন দিকে? r cap cross beta r cap cross beta dot, এটা কি করে বিটা ডটের দিকে হবে?
স্যার বিটা ডটের সঙ্গে 90 মাইনাস থিটা অ্যাঙ্গেল করে দাও।
বিটা ডটের সঙ্গে
90 মাইনাস থিটা।
তার মানে এটা কি হলো? অত কমপ্লিকেট করে ভাবছো কেন? 90 ডিগ্রি মানে বিটা ডটের সঙ্গে 90 মাইনাস থিটা অ্যাঙ্গেল করে থাকে, ঠিকই বলেছো। হ্যাঁ, কিন্তু বেসিক্যালি এটার সঙ্গে পারপেন্ডিকুলার হবে, তাই না? আর এর সঙ্গে পারপেন্ডিকুলার হবে, তার মানেই তো এটা তুমি যেটা বলছো 90 যদি পারপেন্ডিকুলার হয় আর এর সঙ্গে, তাহলে এটা বিটার সঙ্গে 90 ডিগ্রি মাইনাস থিটা হবে, ঠিকই বলছো তুমি। হ্যাঁ, তার মানে বেসিক্যালি যে রেডিয়াস ভেক্টরটা তার উপর পারপেন্ডিকুলার হবে, যেদিকে ফিল্ড পয়েন্টটা আছে তার সঙ্গে পারপেন্ডিকুলার হবে কে? এটা এই ইলেকট্রিক ফিল্ডটা রেডিয়াস ভেক্টরের সঙ্গে পারপেন্ডিকুলার হবে। তার মানে যে ইলেকট্রিক ফিল্ডটা অ্যারাইজ করছে because of this moving point charge, that will have a direction which is perpendicular to the this r vector, this curly r vector, which is pointing towards from the field point, this source point to the field point, তার সঙ্গে পারপেন্ডিকুলার হবে, এটাই বলতে চাইছি আমি, right? Now once you simplify this further, you can also, I can write এটাকে যদি ভি লিখি, ভি লেখার দরকার নেই, বাট এখানে let me write down v 4 pi epsilon 0 c square, and then I have কি থাকবে r cap dot ভি ডট, বা এটাও রেখে দেওয়া যেতে পারে, কিছু যায় আসে না, r cap মাইনাস এটাও ভি ডট, r cap মানে 1 ভি ডট divided by curly r. This is electric field. Now you see, I don't need to calculate magnetic field separately, because what is the pointing vector? Pointing vector মনে আছে sr is 1 over mu 0 কি হবে er cross br. If I take er cross br, again you see br is known to us in terms of er, কি জানি আমরা? So br is কি আমরা আগে লিখেছিলাম, একটু আগে br কি লিখেছিলাম, এই যে br হচ্ছে, this is br. So let us put it here. That will be 1 over mu 0 c times er cross r cap cross er. তাহলে যদি সিম্পলিফাই করা হয় কি দাঁড়াবে জিনিসটা? 1 over mu 0 c into a cross b cross c, তাহলে again b e r square r cap, আমি একবারই করে দিচ্ছি, মাইনাস ই আর dot r into er, right? Now it should be clear why I discussed about this. You see, er dot r, what is er dot r? Because electric field er, I already told you why it is perpendicular to r. So if I take er dot r, the second term will be কি হবে? এটা জিরো হবে, অর্থোগোনাল, রাইট? সো দিস উইল বি জিরো, সেকেন্ড টার্ম ইজ জিরো, রাইট? তাই জন্যই আলোচনাটা করলাম আমরা, রাইট? জিরো। তাহলে কি পড়ে থাকছে? পয়েন্টিং ভেক্টর হচ্ছে সিম্পলি 1 ওভার মিউ 0 সি ইন্টু ই আর স্কোয়ার। তার মানে আর বেশি কিছু খাটতে হবে না আমাদেরকে, ইলেকট্রিক ফিল্ড এক্সপ্রেশন পেয়ে গেছি, এটা স্কোয়ার করলেই হবে। আর ক্যাপ কোন দিকে? পয়েন্টিং ভেক্টর আর ক্যাপ মানে কোন দিকে? towards the field point, from the moving point charge to the towards the field point, এদিকে রেডিয়েশনটা যাচ্ছে, right? That is the energy radiated per unit area per unit time. And so we just have to multiply 1 over mu 0 c with er square to get the pointing vector. So that's an easy task. Let us do that. Okay, so sr, the radiation SR is how much? 1 over mu 0 C E R square R cap. আমরা ER টা কি বার করেছি? Let us write down that ER equal to কি ছিল? একটু আগে বার করেছি। ER is how much? Q over 4 pi Q over 4 pi epsilon 0 C square times R cap dot V into R cap. It's not R cap minus V dot divided by curly R. This is the electric field. Simplified expression under the approximation that velocity is much smaller than the speed of light. Right. That is, it's a non-relativistic case. Accelerating, but with non-relativistic velocity. Right. So if I take a square of that, it will be simply 1 over R cap is there. R cap by mu 0 C. R cap divided by mu 0 times C into, let us take a square, Q square divided by 4 pi epsilon 0 C square whole square, and then whole square of the entire thing, R cap dot V into curly R minus velocity acceleration divided by R square. So A plus A minus B square. So let us simplify it. R cap divided by mu naught C. Let us simplify it a bit further. 1 by epsilon 0 C square, or maybe C square. I can break this into two parts. Let me write down it to be Q square divided by 4 pi epsilon 0 C square. So epsilon 0 square is there, C square. So 4 pi epsilon 0 C square. So I have to introduce an epsilon 0 here. So epsilon 0 square, mu 0 1 by mu 0 C, that will be Q square times 4 pi epsilon 0 C whole square. That will be mu. So I have to multiply mu 0 and epsilon 0 here. Right. I have a mu 1 by mu 0 C here. Right. And then everything else, R cap dot V dot square plus okay, simply scalar V dot square V dot square minus twice R cap dot V dot into R cap dot V dot divided by R square. I'm just taking square of that. Actually, in some book you will find that the CGS unit is used. In some book you will find the SI unit used. So to just compare the results from different books, I used to write this factor separately. 1 by 4 pi epsilon 0, keep it outside the whole entire expression. So that is basically conversion. 1 by 4 pi epsilon 0. Then I have Q square by 4 pi C cube, and then let us simplify this. R cap dot V dot square, and we have minus 2 R cap dot V dot square. So there is 1 R cap square. So I have V dot square, and then minus there is a cos theta term. We already know that the acceleration vector and the radius vector that makes an angle theta. এই ছবিটা একটু আগে এঁকেছিলাম। এদিকে acceleration V dot, এদিকে R cap, angle is theta, একটু আগে বলেছি। তাহলে cos theta term আসবে একটা এখানে, তো মাইনাস কি আসবে V dot square cos square theta, right? And then divided by R square. You can mix things up, but again I prefer to write separately in this way, right? It's up to you. Then take a V dot square common. We shall have R cap divided by 4 pi epsilon 0, then Q square V dot square if I take it outside, and then we have in the denominator 4 pi C cube, okay, bracket, okay, 1 minus cos square theta, that is sine square theta, divided by R square, right? Again, if you want to write down this in terms of acceleration, you can write, okay, maybe you can write, okay, anything. Anyway, this is fine. This is acceleration, V dot is acceleration. So you see, if I ask you what is the direction along which the radiation is emitted from this moving point charge? This is the pointing vector SR. It is a vector, of course, I told you that is along the radius vector, but it has a theta dependence. You can see clearly from here. So I told you that the moving charge, if this is the direction of say acceleration, charge particle is suppose moving in this way, right? Acceleration in this way. And what is theta? Theta point can be anywhere, here, anywhere. Field point can be anywhere. So the angle between the acceleration vector and the this radius vector is theta, right? Now it is sine square theta. So if the charge particle has an acceleration along this direction, along say this x-axis, any axis, any direction, then it will be emitted in a particular fashion. So you see sine square theta, right? When the angle is very small, suppose the field point is here, okay, so then the radius vector will be this, right? Theta. Theta is very small. The radiation will be negligible, right? Theta is very small. So when the sine square theta will be maximized along the orthogonal direction, that means it will be emitted along a particular preferred direction. For a non-relativistic arbitrarily moving point charge, accelerated point charge, the radiation that you will get, see this is a pattern which you should get from this. So there will be two lobes in the orthogonal direction, sine square theta. Why kind this kind of lobe that you can understand? See the length of the this is representing the amplitude. So see gradually this will increase, and then this is maximum. Then this will decrease, and then gradually it will vanish towards this direction, right? So along the motion, or I should not say motion, along the direction of the acceleration vector, there will be no radiation, right? The entire radiation will be emitted in the orthogonal direction. And of course, this what I have drawn on the screen is a cross section. It's a two-dimensional diagram. If you really want to visualize how the radiation pattern should look like, then you should think about all possible direction. For example, the field point should be also above the screen. Here I cannot show it here in the computer screen, but it could be anywhere in the three-dimensional space. If that is the case, then for each and every direction you should get such a lobe. So if you combine all those lobes in three dimension, you will finally get a toroidal shape. That is something like, what is that called, donut shape. I mean, I cannot really draw it in this. So what you will get something like this. Okay, maybe I'm trying, but I cannot really draw it. It's a donut shaped. Right? This is the acceleration vector A. This is some arbitrary direction, say r cap. This is theta. So this is a two-dimensional diagram which is showing you a cross section. If I take a cross section, then you see this part look like this, and then this part look like this, right? So this is possible along each and every direction around the point charge. So that's why it will look like a donut shape, right? Donut shape pattern perpendicular to the direction of acceleration. So the moving point charge is accelerating along this direction, and the radiation is emitting along all the orthogonal direction in a shape of a donut, right? So this is the case of non-relativistic accelerating point charge, and in this case no power is radiated in the forward or backward direction. It is entirely emitted in a donut about the direction of instantaneous acceleration. So this is what this formula is telling us, right? Now we should also know how much time we have. Okay, 6-7 minutes. Now, okay, let us see. So remember this dependence, sine square theta divided by r square, right? And it depends on the acceleration square, a square. All the other things are constant, 4 pi epsilon 0 c q, everything is constant. The most important thing that you should remember, that pointing vector is proportional to the acceleration square times this sine square theta by r square, which is basically giving you the directional dependence of the radiation pattern. And if I ask you calculate now the total power radiated, we have discussed about this a couple of minutes back. So what you need to do, you just have to integrate. Okay, if I ask you calculate the total power emitted by the starting point, total power emitted, total power emitted, right? Let us call that PT, total power emitted. So how do you get that? You just have to integrate over the surface area of the sphere. So imagine a sphere of radius this curly r, and then it's a closed sphere, right? So we just have to integrate over the area. It's a closed surface. So SR is the pointing vector. You take a dot product r cap dA. That means what I'm trying to say. So suppose the moving point charge, this is the moving point charge. You have this, the field point P, this is R. So imagine a sphere of radius R, right? So you have element of area along each direction. Some element of area is covered, and you have a direction. This r cap is what? R cap along any direction. This r cap is what? Along the ortho normal to the sphere. This is r cap. This is r cap, and this is the area dA. So the vector area is basically given by r cap dA, or you can write dA vector, that is given by r cap times dA. Right? If you take a dot product of the pointing vector with this, because for any other kind of arbitrary surface, you have to take this angle appropriately, because in that case they will not be orthogonal. I can imagine any other arbitrary surface, but in that case the r will be different along different direction. If I imagine a sphere, r is same along all the direction, right? So that's a symmetric surface that we have imagined. So total power emitted around this moving point charge is given by this expression. So let us do this integral. That is quite straightforward, because this r, if you remember the expression for, let us do this. So we have three variables. It's area, so only two variables. Area means change korche theta or phi, তাই না? So theta goes from 0 to pi, phi goes from 0 to 2 pi. We are integrating over the surface area, this sphere, and then we have this pointing vector which you have derived in the last page, 1 by 4 pi epsilon 0 q square into v dot square. Let us write the acceleration square by 4 pi c cube into sine square theta by r square. And then what is this area? You have a dot product here. You see this was also along r cap. So r cap dot r cap is 1, right? This pointing vector was pointed along r cap, and we have a dot r cap. So r cap dot r cap is 1. And what is this area? Element of area, the surface of a sphere, r square sine theta d theta d phi. You see this r square will cancel out, right? So what we are left with, and again you see there is only function of phi, d phi. So you can integrate d phi. That will be simply 2 pi. So 1 over 4 pi epsilon 0 q square a square by 4 pi c cube. Phi ইন্টিগ্রালটা করলে পাওয়া যাবে 2 pi, আর থিটা ইন্টিগ্রালটা পড়ে থাকলো sin cube theta 0 to pi. sin cube theta তোমরা ইজিলি ইন্টিগ্রেট করতে পারবে। sin square theta into বিভিন্ন ভাবে করা যাবে। sin square theta is 1 minus cos square theta, so sin theta into 1 minus cos square theta, then just integrate and put the limit 0 to pi. It will come out to be around it will be 4 by 3. I'm not doing that. Everyone of you can do this. So this will be 1 over 4 pi epsilon 0 q square a square divided by 4 pi c cube into 2 pi, and this integral will give you 4/3. If you simplify this further, you will get 1 over 4 pi epsilon 0 q square a square, no 2 আসবে একটা 2 থাকবে, 4 আছে, 4 4 কেটে যাবে, 2 হ্যাঁ, twice q square a square by 3c cube. Okay, and this is the expression for total power emitted by an arbitrarily moving point charge at in the non-relativistic regime. And this formula has a name. It's a famous formula. It's called Larma radiation formula. This formula is called Larma radiation formula. So this is an important formula that you have to use in future calculation. This is the power emitted by non-relativistic moving point charge at any direction. This is the expression for radiation. I think we do not have any more time, so I stop here. If you have any question, I can take one or two quick questions. Okay, if you do not have any question, we can continue from this point in the next class. I know you have other classes.